Imagine a tech company aggressively marketing a new smartphone. Their main selling point is a battery that lasts an average of 50 hours. An independent testing group decides to verify that claim. They take 20 of these phones, turn them on, and leave them until they go flat. The results show that most of the phones die much earlier than the marketing promised. Look at the raw results. 17 of them fall short. Exactly 3 actually reach that 50-hour mark. That's a success rate of only 15%. If 85% of the actual products fail to meet the standard, how is the company legally allowed to claim a 50-hour average? The secret is in the arithmetic mean. This is the mathematical center of balance for a dataset, found by adding up every single value and dividing by the number of items in the sample. If we check the test group, 19 phones died around the 45-hour mark. But there is a hidden culprit, one freak battery that somehow lasted 142 hours. The mean calculation is indifferent to the typical experience. It weighs every hour equally, allowing that one massive outlier to drag the final average up to 50. Relying on a single average in a world of outliers results in an incomplete understanding of the data we're looking at. Our first defense against outliers is the median. To find it, we simply line up the data from smallest to largest and find the midpoint. When we sort the 20 battery lifespans in order, the calculation identifies the exact middle value as 46 hours. The median is robust. If our outlier battery lasted 1,000 hours instead of 142, the physical middle number of our lineup would not change. The distance between the mean and the median creates skewness. Whenever these two numbers are vastly different, it serves as an alarm that extreme values are pulling the average away from the center. While finding the true middle protects us from outliers, it still doesn't reveal how the rest of the data is behaving. We can test our statistical tools on a completely different scenario, evaluating the physical makeup of two competing basketball teams. On paper, Team I and Team 2 share the same summary statistics. They have the exact same average height of 75 inches and the same median height of 76 inches. Look at the composition of Team I. These players are all relatively similar in height, tightly packed between 72 and 78 inches. But Team 2 is built on extremes. It features a 67-inch player standing right next to an 84-inch giant. Two datasets can look identical at their center points while representing completely different physical realities. To understand those realities, we have to measure dispersion, how far the data scatters away from the middle. You could use the range, but that only looks at the highest and lowest endpoints while ignoring the rest of the group. Instead, we use standard deviation. It calculates the typical distance that every single piece of data sits from the center point. This comparison shows the difference. Team I has a tight standard deviation of 2.4, while Team 2 sits at over 6.2, mathematically proving their heights are more varied. Standard deviation reveals how much a group actually resembles its own average. A low number indicates predictability, while a high number reveals underlying variance. We face one final challenge. How do we measure scatter when comparing two things on completely different scales? Consider salary data. Undergraduates earn roughly $4,800 on average, while corporate graduates average nearly $80,000. The standard deviation for the graduates is over $21,000. On its own, that looks massive, but that is largely because their baseline salaries are so much higher. The coefficient of variation, or CV, standardizes the scatter by converting it into a percentage relative to the mean. When we apply the CV, we see the real relationship. The undergraduate salaries are actually twice as volatile and unpredictable as the corporate ones. Analytical comparison requires adjusting our mathematical lens to account for the underlying scale of the data. Every dataset is defined by 3 distinct dimensions: its center, its spread, and its physical shape. The next time you see a simple average in an advertisement or a news article, look past the single number. Ask for the median to find the true middle, and the standard deviation to see how much that middle actually matters. Until you can see the complete anatomy of the numbers, you are only seeing half the story.